We've looked at two ways that we can use these formula. This example here shows us yet another way that we might be using these formulas to help us get information. In this example, we are given the sine of two different angles. We're told that the sine of one angle, we'll call it alpha, is 4 over 5, and the sine of another angle, beta, is 1 over 2, 1/2. We also are told that this first angle alpha is in Q2, quadrant 2, and this angle beta is in quadrant 1, Q1, which is important information because we'll recognize we're going to have to give things either positive or negative values. And our mission is to find the cosine of both of these angles, and then we're going to use that information to find the cosine of alpha and beta, so the new angle we get when we add these two, and then the sine of the new angle we would get if we added these two angles. So we're never really going to find out what this angle alpha plus beta is. We don't really care so much about what the angle is. What we want to know is the trig value for that, either sine or cosine. So to get started, let's recognize here that the sine of an angle represents, sine is y over r, or y over hypotenuse. In this point example, I'm going to use r as the radius. And again here, this represents y over r. So to help us find this information, I think that it will be useful to recognize if we want to draw a triangle here or think about it. I'll draw the triangle just to help us visualize it. So here we have a triangle, and this is going to be our angle. Here is going to be our alpha. And y, this is going to be 4, and our hypotenuse is 5. And we need this information here. So we can do this using the Pythagorean theorem. So here I'm going to call this x, this adjacent side, x. So to use the Pythagorean theorem to help us solve, we have x squared plus 4 squared is equal to 5 squared. X squared plus 16 is equal to 25. X squared, 25 minus 16 is 9. Take the square root of both sides. X is equal to 3. And then the cosine of this angle alpha here, put it over here, the cosine of our alpha is adjacent over r, and our adjacent x is 3. So let me write that, x over r, which is 3 over 5. But now we have to consider, is this going to be positive or negative? So going back up here, we're told that alpha is in Q2. And in Q2, our cosine is negative. So this is going to be negative 3/5. Now we have our other angle to consider. So here it's going to be, I'm going to call it beta. I mean, I know somebody's probably saying, oh, these triangles look pretty much the same. Just we're using it to help us get an idea of what's going on here. And our sine is, in this triangle, is 1, and our radius here is 2. And again, we need this x. So again, we'll use the Pythagorean theorem to help us find it. And so we have x squared plus 1 squared equals 2 squared. X squared plus 1 is equal to 4. Subtract 1 from both sides. We have x squared equals 3. Taking the square root of both sides, we have x is equal to the square root of 3. And now, again, we did this so we can evaluate the cosine. So the cosine of beta is x over r. X is square root 3, and our r is 2. So the cosine of r beta is square root 3 over 2. And this is our beta is in Q1. In Q1, all trig functions are positive. So we are done here. This would be positive. So we have the pieces. Now we are going to use our formulas. So we need cosine of alpha plus beta. So cosine of alpha plus beta, I'm going to write the formula. So the more you see it, you'll be more comfortable with it, and maybe you'll even remember it. It's the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. And now we know that our alpha, well, we don't know our alpha, so we can't even name it here. So we'll just go right to our substitution. So the cosine of alpha is negative 3/5. So we have negative 3/5. The cosine of beta is square root 3 over 2, which, oh, by the way, that's an angle that you should know, even though we're not asked to name it. And now we have the sine, let me put these like this so we don't mess up. The sine of alpha, which was given to us, that is our 4 over 5. And the sine of beta, which was also given to us, is 1/2. So there are our angles. And now for the multiplication, negative 3 times square root 3 is negative 3 square root 3. 5 times 2 is 10. And then over here we have 4 times 1, which is 4, and 5 times 2 is 10. Similar to before, the denominators are the same, so we can combine the numerators, and we have negative 3 square root 3 minus 4 all over 10. And that would be our answer for the cosine of adding these two angles. Now, let's look at the sine of these two angles. Just ignore the phone in the background. It's my husband telling me he's coming home for dinner. So now we need the sine of alpha plus beta, and this is going to be equal to the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. So if you look on the sheet, you'll see this is the formula. I just wrote it down here. And now we have the sine of alpha, which is our 4/5, the cosine of beta, which is our radical 3 over 2, and now the addition, the cosine of alpha is negative 3 over 5, and the sine of our beta is 1/2. So doing the multiplication, 4 times the square root of 3 is 4 square root of 3. 5 times 2 is 10. Whoops. And then over here, negative 3 times 1 is negative 3. 5 times 2 is 10. So there is our answer. And as we've been doing in these, when the denominator is the same, we are able to combine into one fraction. So we have 4 square root 3 minus 3. And that would be our answer. So we're able to use these formulas to help us find the sine function of something by breaking up the original angle into two pieces and either adding or subtracting, or we might be given the information for two separate angles, as in this problem here. We were given the information for two angles, their sine function. We use that to find their cosine partner, and then we're able to find the sine and cosine of these angles, putting them together. Notice, we never found out, I mean, we could have found out what B was. We never named the angles themselves. We just ultimately wanted the sine and cosine function.